Finding an explicit formula. Thus far, we have been given the explicit formula and asked to find a number of terms of the sequence. Sometimes, the explicit formula for the nth term of a sequence is not given. Instead, we are given several terms from the sequence. When this happens, we can work in reverse to find an explicit formula from the first few terms of a sequence. The key to finding an explicit formula is to look for a pattern in the terms. Keep in mind that the pattern may involve alternating terms, formulas for numerators, formulas for denominators, exponents, or bases. Now, given the first few terms of a sequence, we want to be able to find an explicit formula for the sequence. Number one, you're going to look for a pattern among the terms. Number two, if the terms are fractions, look for a separate pattern among the numerators and denominators. Number three, look for a pattern among the signs of the terms. And then write a formula for a subscript n in terms of n. And then test your formula for n is equal to 1, n is equal to 2, and n is equal to 3. So for example number 4, we're writing an explicit formula for the nth term of a sequence. Write an explicit formula for the nth term of each sequence. So look for the term in each sequence. So for the first part A, here are the first 5 terms of the sequence. We have negative 2 over 11, 3 over 13, negative 4 over 15, 5 over 17, and negative 6 over 19. So I want you to look at this before you look at steps 1, 2, and 3. If you look at this, we have an alternating sequence because the signs are changing. The first one is negative, the second term is positive. The third term is negative, the fourth term is positive. The fifth term is negative. So, number one, the terms alternate between positive and negative signs. So we can use negative 1 to the nth power to make the terms alternate. Next, if we take a look at the numerators, it goes from 2 to 3 to 4 to 5 and to 6. So for each term, we're increasing it by 1. 2 plus 1 gives us 3. 3 plus 1 gives us 4. 4 plus 1 gives us 5. 5 plus 1 gives us 6. So for part 2, the numerator can be represented by n plus 1 because we're taking each n and adding 1 to that. Now if we look at the denominator, we have 11, 13, 15, 17, and 19. So what's happening here is that it's increasing by the value of 2. So the denominator can be represented by the following: 2 times n plus 9. Now, if we take a look at the formula, we have a subscript n, which is going to equal negative 1 to the nth power times n plus 1 over 2n plus 9. So if we take a look at the 11, right? Well, if we use the value of 2, okay, if we use if we use 1, if we put in 1 in for n, negative 1 to the nth power is negative 1. If we put in 1 plus 1, that gives us 2. And 2 times 1 is 2 plus 9 gives us 11. If we go to the second term, we put in 2. Negative 1 to the second power is positive 1. 2 plus 1 gives us 3. And then 2 times 2 is 4 plus 9 gives us 13. Let's do one more. If we plug in the third term, which is 3, negative 1 to the third power is negative 1, so we know it's negative. 3 plus 1 gives us 4. And 2 times 3 is 6, plus 9 is 15, so it matches for the first 3 terms. In part B, we have negative 2 over 25 for the first term, negative 2 over 125, negative 2 over 625, negative 2 over 3,125, and negative 2 over 15,625. Now the terms are all negative, so it's not an alternating sequence, okay? And so therefore we know it's always going to be negative, so the negative is going to be fixed. We know that the numerator never changes because the numerator is always 2, but we can notice that the denominators are multiples or increasing powers of 5. So that's 5 squared, 5 cubed, 5 to the 4th power, 5 to the 5th power, 5 to the 6th power, 5 to the 7th power, and so on. So therefore, we know the fraction is negative because it's always negative. We know the numerator is always going to be 2, and the denominator can be represented by the following: 5 to the n plus 1. If we let the first term be 1, therefore 1 plus 1 gives us 5 squared, and that's how we're getting 5 squared to be the first term. Next, C. We have e to the 4th, e to the 5th, e to the 6th, e to the 7th, e to the 8th with an ellipsis. Now, the terms are powers of e, so we know the base is going to be e. So for when n is equal to 1, the first term is e to the 4th. So the exponent must be n plus 3 because 1 plus 3 is going to give us 4. So a to the n is going to equal e to the n plus 3. If we find the second term, a subscript 2, 2 plus 3 is going to give us 5. If we want to find a third term, 3 plus 3 is going to give us 6, and so on.